All right, so our lesson today is going to be on inverse trig functions. We're going to learn how to take derivatives, take integrals, but first we're going to study just what these things mean, what they look like, what the functions graph as, why we can even do it, what the domain is, what the range is. We're going to start with just the idea of what a trig function is. Now I want you to think about what it means to be an inverse compared to a function. There was one qualification that we had to have in order to guarantee that we actually could find an inverse. A function had to be this in order to have a inverse. What?
1 to 1.
It's got to be 1 to 1. Now, I want you to think of trig functions, all the ones that you know. Are trig functions 1 to 1?
Is tangent considered 1?
Well, tangent does this, but then over here it does this.
So you have to restrict the domain then?
That's right. What about sine? Is sine 1 to 1?
From 0 to pi?
Heck no, it does this all the time, right? And so does cosine. But if we do restrict the domain, then we can change these functions into something that can have an inverse. So, if we think about trig functions in general, no, they're not 1 to 1. But if we restrict the domain, then we make them, we kind of force them to be 1 to 1 for a little area, which means that our inverses of trig functions are going to have very specific domains. Does that make sense to you? So we're going to talk about inverses of trig functions, but only on certain domains. Not for the whole thing, because you can't do that. Then it would not be, the inverse won't actually be a function. So we need to restrict domain, then we can have inverse trig functions. Let me give you an example here real quick. So if we look at y equals sine x. Well, if you remember what y equals sine x looks like, does this one start at 0 or start at 1? Yeah. So this looks okay. Here's 1 and negative 1. Where's it peak? Do you remember?
Pi over 2.
Mm-hmm. And our function goes up, peaks, hits 0 at pi, goes down, bottoms out, hits 0 at 2 pi. So we get this, that looking graph. Obviously that, hopefully to you, is not 1 to 1. It does not pass the horizontal line test. In fact, no portion of this, unless we go from here to here, is actually 1 to 1. We don't want to consider that. So we're going to take this function and even go a little bit left with it. So if we go left a little bit, say negative pi over 2. What's sine of negative pi over 2?
-1.
Yeah. That would be down here. The idea is, let's not consider sine for the entire domain, because obviously it's not 1 to 1. And in order to find an inverse, we have to have a function that is 1 to 1. So what we've done to make these things easier, to not have a domain that's way over here, to have a domain that's kind of nice for us to work with, that has a 0 in it, because we like to have domains with zeros in it, it's really nice. What we say is, no, we're not going to consider from here to here, because that's obviously not 1 to 1. From here to here is 1 to 1, but it's not a nice domain that we like to work with. Past that, it's not 1 to 1 anyway, but right here, between negative pi over 2 and pi over 2, we're going to eliminate all this other stuff and focus on this domain. So if we focus on the domain and restrict it to negative pi over 2 to pi over 2, do you guys see that sine becomes 1 to 1 on that domain? Yes, no?
Yes.
Okay, good. So, y equals sine x, cool. On the domain of negative pi over 2 to pi over 2, is 1 to 1. And that's what we want. Again, if a function is 1 to 1, it must have an inverse. Therefore, we say, okay, cool, well, we can find an inverse on this domain. And what I'm going to do is, I'm going to rewrite this just a little bit. I'm going to get rid of all this stuff. If sine is 1 to 1 on that domain, then we can find an inverse for it. And what we're going to do is, for the rest of our time in this little subsection here, I'm going to give you an original function, trig function. We're going to talk about the inverse. So what the domain is, what the range is, and then what the inverse is, domain and range is. You guys ready for it? So with sine, what's the domain again?
Negative pi over 2 to the power of 2.
Cool.
Range negative 1 to 1.
That's right. Do you remember what the difference between brackets and parentheses are?
One's
Brackets include it, and the parentheses don't include it. So, domain is this. Range, I'm sorry, what was the range one more time? Perfect. Oops. I just went over that too, huh? Brackets. Includes it. Now, if we talk about the inverse, remember what inverse does. What an inverse does is it switches the x and the y. It switches the domain with the range. So a couple notes that we have. Just a few of them. So a little bit of a note here. First one, we're going to use this in a little bit, not right now, but in a little bit. Y equals sine inverse of x if and only if sine of y equals x. That's the only way we can have this. So inverse functions work where we switch our x into y. So y equals sine inverse of x if and only if sine of y equals x. Also, a couple other things. Inputs get interchanged with outputs, which means that domain gets interchanged with range. So if this is our sine y equals sine x, then we should be able to find an inverse for it. Let's talk about it. I'm going to make that a little bit bigger so you can see it better. Okay, so a couple important things. Again, since this is one-to-one, we have to find an inverse. Since we know about inverses already, they're reflections across the diagonal y equals x. What that means is that our inputs change with our outputs. Our x's become y's, our y's become x's. So let's look at this from our domain and range and see what we can get for our picture over here. From our points, see what we can get for our picture over here. So if the point pi over 2, 1, if the point pi over 2, 1 is on my original graph, the point 1, pi over 2 will be on my inverse graph. Does that make sense? Pi over 2, 1's on this one, therefore 1 comma pi over 2 is here. Does that make sense to you? Mm-hmm. If negative pi over 2, negative 1 is on my original graph, on the inverse, I should have negative 1 comma negative pi over 2. If 0, 0 is on my original graph, 0, 0 is also going to be on my inverse. Now, right now it looks almost the same, but the curve is a little bit switched. Notice if I reflect this, it's not going to be doing this anymore, it's going to be doing this. It's not going to be doing this anymore, it's going to be doing this. And that's the way this inverse sine looks. So our inverse sine function looks like that. About like that. I'm not the best artist in the world, but hopefully you get the picture here. Show of hands if you feel okay with that one. So with our inverses, we can find them just from our original functions by interchanging our x's and our y's. Now, also let's talk about the domain and the range of these. This is going to be important for you. You do have to consider the domain and the range of your functions and your inverse trig functions. So, tell me something about the domain. What's the domain of our inverse sine, or sine inverse?
-1.
Perfect. So, with sine inverse, we're not talking about plugging in pi. That's out of the domain. We can only plug in from -1 to 1. Do you understand? Look it. If you can only get out, think about sine. When you plug in anything to sine, all you can get out is between -1 and 1, right? If range becomes domain, that means for inverses you can only plug in -1 to 1. You can't plug in anything bigger than that, or smaller than -1. You guys getting the idea here? So our domain is for sure -1 to 1. How about the range?
Pi over 2 pi.
That's right. Basically, these just switch. Now we're going to use the same idea. We're going to go a little bit quicker through this since I've already explained the idea of being one-to-one. We're going to define a section of a trig function that is one-to-one. And we're going to start switching around the x and the y. Then we're going to switch the domain with the range and get the domain and range of our inverse functions. Are you guys okay with this one before we go on?
Yes.
Okay, let's keep going then. How about cosine? Where's cosine start? Okay, so if we went any further this way, we'd have something that's not one-to-one. So we're going to start this domain of cosine at 0. So domain normally does this. We don't want that. So we're going to ignore everything but the range from 0 to, what's that one? Good. What's this one? So we want 0 to pi. So we don't care about this. We don't care about this. Firstly, did we define a section of our graph that is one-to-one?
Yes.
Yes, yes. Okay. Tell me the domain that we're going to be working with for our cosine. Yep. So we have 0 to pi. And the range of this little one-to-one section is... Good. This is still -1. This is still 1. So -1 to 1. Quick head nod if you're okay with that one so far. That's just your regular cosine. Now let's make it inverse. Because it's 1-to-1, we know that we can do this. So let's see if we can do it. Tell you what. If the point 0, 1 is on my original function, if 0, 1's on my original, what's on my inverse?
1, 0, 0.
Perfect. That's there. If pi -1 is on my function, what's on my inverse?
0.
If 1, 0 is on my function,
0, 1.
and we get something that looks like this. Wow, that's really nasty. Sorry, I hope you get the idea of it. My graphs are not that great. Oh, so you know what? That's why. That's Mr. Leonard being silly. I made a mistake here. Did you catch my mistake? I hope that you did. I made a mistake here. I said something wrong. I want you to catch it. I said 0, 1 is on this graph. Is 1, 0. Is 1, 0 on that graph? No, what is that actually? Probably would have made it better if I would have put pi over 2. Yeah, so, which is why I got a funny graph over here. If pi over 2, 0's on my graph, then 0, pi over 2. Remember, this is pi, and this is right between pi over 2. That looks a little bit better. My mistake on that. Let's talk about domain and range. What's our new domain for our inverse function?
-1, 1.
Yep. How about our range?
0 to pi.
0 to pi. These two just switch. We still okay with these ones? Okay, we got several more to do, so we're going to kind of kick it up a little bit. Let's talk about tangent. Now, naturally, tangent does this repeating thing, right? It's those S-curves that repeat over and over and over again. So hopefully for you, it makes sense that we're going to define this between -pi over 2, where we have an asymptote, to pi over 2. Tangent looks about like that. Now, since this is 1-to-1 on that domain, our domain is -pi over 2 to pi over 2. Someone out there tell me, should I use brackets for this or parentheses for that?
Not included in the asymptote.
Okay. Because I can't actually get there. Now our range is interesting. It's a little bit different from before. What's our range?
Oh.
That's right. It's forever. So negative infinity to infinity. Which means for our inverse, we can find it is 1 to 1. Here's what happens with this. Of course, 0, 0, hopefully you see this, 0, 0 is on original, 0, 0 is going to be on the inverse. If I have asymptotes at x equals pi over 2 and x equals negative pi over 2, on the inverse I'm going to have asymptotes at y equals pi over 2 and y equals negative pi over 2. Does that make sense to you? So this graph is going to be reflected. That includes our asymptotes. So here's pi over 2, negative pi over 2. Now what this one says is that as we approach x equals pi over 2, we approach y equals positive infinity. Did you see that? That means as we get y closer to pi over 2, x is going to approach positive infinity. So we have this look. And that's our inverse function for tangent. Okay, quick show of hands, feel okay with these ones so far? Do you have this written down? Because I got to erase it. But we are going to reference this. So keep in mind the domains of these things, okay? I'm going to be referencing the domains of sine and the domains of sine inverse a lot. And so same thing with cosine and tangent. I'm going to try to fit the 3 remaining ones over here so we can use them. But keep these things in mind. Okay, what's the next one we got? What do you want to do? Yeah, we can do cosecant. We start with sine, may as well do cosecant. If you've forgotten how cosecant looks, it's those ones with the u's. That's like if you took sine and exploded it. And so instead of doing this, it does this. So it has these u's everywhere. Here's how it looks. We have 1 and negative 1. So we're still touching that, but we're not between 1 and negative 1. We're outside of it. We got pi over 2. We got negative pi over 2. And they look like this. Now, are those 1 to 1?
No.
No, not even close. So if they're not 1 to 1, we've got to erase some of this graph. What we're going to choose to do is we're going to keep our domain as simple as possible. Our domain's going to stick right here. We're going to erase this and that. So really what we're looking at is just this piece of the graph. This piece and this piece. That's going to be the domain that we restrict for cosecant, because otherwise we don't have a 1-to-1 function. You guys all right with this so far? Now let's look at what the domain of this thing actually is. Our domain. What is our domain? What can we plug into this?
All the number.
Plug in.
Between
Negative
2.
Okay, we start at negative pi over 2. You guys see that, right?
0.
Oh, okay, so negative pi over 2. Can we actually plug in negative pi over 2? Can we plug it in?
Yeah.
Yes, there's a point there. Where do we go to? Can we actually plug in 0? That's a problem. So we're going to go to 0. We're going to put a little parentheses there saying, I can't plug in 0. Do you guys see why we can't plug in 0? We have an asymptote here and here. We can't plug that in. But we can start just on the other side of 0 and go to where? Oops. And we can actually get pi over 2. So we can basically plug in anything between negative pi over 2 and pi over 2 except for what number? Yeah, that's the idea. Now, let's talk about the range. Negative, I'll give you negative infinity. I like the negative infinity. Negative infinity up to where do we stop?
Negative 1.
Negative 1. Can we actually get the negative 1?
Yeah.
Yes. Now, is there anything between negative 1 and 1?
No.
So we got to pick this thing back up again at 1 and go to positive infinity. What that means for our inverse is that our domain and range are going to switch. So when we do y equals cosecant inverse, it's a little weird to think about, but here we go. We'll start off kind of simply. I'm going to erase these because those are irrelevant for us. If we have pi over 2, 1 on this graph, then 1 pi over 2 is going to be on this graph. If we have negative pi over 2, negative 1, then we're going to get negative 1, negative pi over 2 here. We okay with that? We sure? As we get closer to 0, we're going to positive infinity on the y. So as we get closer to 0, we're going to go positive infinity on the x. And likewise here. And that's a look for cosecant inverse. Tell me what the domain is, please. The domain should be pretty easy for you guys. What's the domain for our cosecant inverse? Say what? Here. Well, yeah, the domain's actually a little bit easier to see for me. Negative infinity to negative 1. Inclusive. 1 to infinity. In fact, it should be exactly this. Our range should be exactly this. And hopefully you can see that it is. Are you guys okay with that one? It's a little weird, right? Well, it was for me the first time I saw it years and years ago. But are you okay with that one? So we know that, hey, pi over 2, 1? No. 1 pi over 2. Negative pi over 2, negative 1? No. Negative 1, negative pi over 2. Infinity at positive y's, infinity at positive x's. That's the idea. I think I'm going to run out of room here on this next one. I'll have to do the other one over here. So let's do, what am I missing? I got sine, cosine, tangent, cosecant. Let's do secant. Secant looks really, really similar to cosecant. It's only shifted over, just like cosine looks really similar to sine. It's only shifted over. So when we shift this over, what we actually get is at 1, negative 1, this looks like that. And this. That's how secant looks graphically. We see that at 0 we got 1, at pi we got negative 1. Can we plug in pi over 2? No. Remember that secant's 1 over cosine, and if you plug in pi over 2 cosine, you get 0. And so if we do that, we'd have something that's undefined. That's where these asymptotes are actually coming from, is the 1 over 0s that we have. So, is this 1-to-1 right now? No, let's erase this and this. And then we do have something that's 1-to-1. From this little piece, we'll erase this whole side. And this little piece, we'll erase this whole side. Can you tell me what the domain is?
Negative 1. Union 1.
Talking about the domain. The domain.
Oh,
We can plug in 0. That's good. Yeah, we can plug in 0, and you can plug it in. Where does it go to? Can you plug in pi over 2? Okay, so no. But then we start up at pi over 2 again, and we end up getting to pi. That's right, and we can actually plug in pi. How about the range? Oh, let's do the range. What can you get out of this thing?
Any number except between 1 and -1.
That's right. So any number between there says negative infinity to negative 1, inclusive, and then 1 to positive infinity. So now we get to go ahead and do the inverse. Here we go. If 0, 1 is on our original graph, then 1, 0 is on my new graph. Let's see. If pi negative 1 is on my original graph, then negative 1 pi is on my inverse graph. If we did a horizontal asymptote, vertical asymptote at pi over 2, we're going to have a horizontal one at pi over 2 for inverse. As we went positive along the y, we were asymptotic to pi over 2. So as we go horizontal along the x, we're going to be asymptotic, and same thing here. I'll make sure I got all these things right. Let's see our domain or range. What's our domain for this next one? Yeah, look at this. Negative infinity to negative 1. And then 1 to infinity. Range should be exactly like this domain. And we've got one more. Which one is it? Cotangent? Let's do that. Do you guys have questions on these two? Do you have these written down? Especially the domain and the range, yes? Okay, cotangent. Cotangent, if you'll remember, looks like a shifted over and inverted tangent. So it still has an asymptote at 0 and at pi. It only looks like this though. Like that. Where our domain is 0 to pi. But not inclusive. And our range is what, please? So with our cotangent inverse, if we have asymptotes, vertical asymptotes at 0 and pi, we got horizontal asymptotes at 0 and pi. If pi over 2, 0 is on our graph, then 0, pi over 2 is on our inverse. Let's see, pi we're doing negative infinity, so pi we're doing negative infinity here. And that's the graph. Sorry about the bad graph on that one, but that's the graph for our cotangent inverse. And we'll do the domain and range and be done with this stuff. It's pretty dry pretty fast. Domain is negative infinity to infinity, and then range is 0 to pi. Oh my gosh, thank goodness we're finally done with those things. What I want to know out of this is, do you understand where the inverses are coming from? Did you see the development of those? I don't want to just give you the inverse, say this is what it looks like, but hopefully you've seen the relationship. Do you guys see the relationship? X's and Y's are just changing. Domains and ranges are just changing. That's the whole idea here. Now, what we're going to do, just to get our heads wrapped around this, is practice a few examples of using some inverses, seeing what it looks like. So we're going to evaluate. Evaluate just means find out the answer of this expression I'm giving you. So let's look at this one. I want to find out what sine inverse of 1/2 is. Sine inverse of 1/2 equals y. How much is y? Think about what inverses are in relation to their original trig functions, and this will help you a lot. So think about it this way. Sine inverse of 1/2 equals y if and only if sine of y equals 1/2. Do you see how to change between an inverse and the original? You just switch your y and your output, your input, your domain, your range, your x and your y. So if sine inverse of 1/2 equals y, well, then sine y has to equal 1/2. Are you guys okay on that switch? Then you think in your head, or you use your unit circle, and you think, okay, well, what angle do I have to plug in here to give me a sine of 1/2? Keep in mind, what's the domain of your sine that we've restricted it to? Look at your domain right now. For sine, what's the domain of the sine? Okay, so whatever you find, it's got to be between negative pi over 2 and pi over 2. So we restricted it to the fourth and first quadrants. Does that make sense to you? So just look there. Look on your unit circle and figure out, okay, what is it?
Pi over 6.
Pi over 6. Pi over 6. What that means for us is that sine inverse of 1/2 equals pi over 6. Notice this. The range of sine inverse was negative pi over 2 to pi over 2, because the domain we restricted for sine is negative pi over 2 to pi over 2. Is this in the in the range of sine inverse?
Yes.
Is it between negative pi over 2 and pi over 2? Okay, so that's one key I want you to understand, is that this had to be the appropriate range of sine inverse and domain of sine, because they're the same thing. It's got to be in the range of sine inverse and the domain of sine. They're the same. In this case, negative pi over 2 to pi over 2. Since it is, we know that we've done this one right. Are you guys okay with that one so far? Are you sure? Are there any questions on that? I want to make sure y'all get it before we go on. Having fun yet? We're not really even doing calculus, huh? Just doing trig right now. Don't worry, we'll get to calculus soon enough. How about cosine inverse of this? So cosine inverse of square root of 3 over 2 equals y. Remember, this is if and only if. Can you restate that on your own? If I say cosine inverse of square root of 3 over 2 equals y, can you tell me what the original, the inverse of that would be? Cosine of... Perfect. Now, look at your papers, look at your notes here, and tell me what is the range of cosine inverse, or likewise, same thing, what's the domain of cosine? 0 to pi. So whatever you find here, whatever this is, it has to be between 0 and pi. That means you restrict your unit circle to the first two quadrants. Remember that? All students, all things are positive, only sine is positive. So cosine, this is probably going to be in the second quadrant, because we have something, oh shoot, you know what, I forgot the negative. Let's make that negative.
Alright, that's fine.
For funsies.
That's fine.
Okay, so if we, you know what, we'll do both. If I didn't have the negative, what quadrant would it be?
1.
Okay, if I do have the negative, what quadrant is it? Oh good, we just learned something. So because this is negative square root of 3 over 2, I'm not thinking first quadrant, I'm thinking second quadrant. I'm not thinking any other ones because that's outside of the domain of this. I'm thinking only 0 to pi. Have you thought about how much that is? Remember that cosine counts up. So cosine counts up square root of 4 over 2, square root of 3 over 2, square root of 2 over 2, square root of 1 over 2, and then square root of 0 over 2. Then it counts back down. Square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. So, but negative. So this one would be... Exactly right. So if we find out that y is 5 pi over 6, then we've solved our problem. Then we know that cosine inverse of negative square root of 3 over 2 is 5 pi over 6. That's the idea here. Are we okay with the idea so far? I know that some of you don't like trig so much. Are you understanding this part of it?
Yeah.
Your unit circle is going to be pretty important, right? Okay, tan inverse square root 3 equals y. Tan inverse square root 3 equals y. This happens if and only if tan y equals the square root of 3. Can you please give me the restricted domain of our tangent?
Negative pi over 2 pi over 2.
Very good. Restricted domain is negative pi over 2 to pi over 2. That means that whatever we find has to be in the fourth or first quadrants. Are you with me on that one? Fourth or first quadrants. All students take calculus. Okay, so fourth or first. Sit it over and over again anyway.
So the right side of the circle.
Yeah, that's right. It's the right side. So can you think of all students take calculus? Tangent is positive in the first and negative in the fourth. We're looking at positive angles here. So this has to be in quadrant number 1. Can you think of what gives you tangent?
Pi over 3.
Pi over 3? Pi over 3?
Yeah.
Yes.
So then y equals pi over 3. That means that tan inverse of the square root of 3 equals pi over 3. So when we look at these things, we first find out, okay, well, translate this back into its original function. Rather than inverse, look at the original trig function, because we're better at that. We have unit circles that help us with that. Then we think about in the domain that we've restricted, what's the appropriate angle that's going to give us this relationship. Find out that appropriate angle, make sure that it is actually the correct quadrant, and then we just restate it. Sine inverse of 1/2 is pi over 6, and so on and so forth. Show of hands feel okay with this so far. Now, if you ever come across something like this, cosine inverse of 0.6. I don't have anything on my unit circle that says 0.6, okay? So what I'm going to do with this, I'm going to use my calculator. So when you get something like this, just use your calculator. You have the cosine inverse on your calculator. Make sure it's in radians. Please make sure it's in radians, and then just do that. Don't do it now. Just try it on your own later. Just use your calculator. So these ones, I don't want you using your calculator here. I don't want to get random, weird decimal numbers. I want you to really work on it. If it's a number like 1/2, square root of 3 over 2, square root of 3, those ones that you see on the unit circle, do it this way. If it's 0.6, 0.234, use your calculator. Am I getting through to you guys on that one? So try doing this. If you can't do it, then use your calculator. Okay, now we're going to continue here. Now what we're going to try is compounding some of these trigonometric relationships. They get a little funky, but I'm going to give you 2 ways to work on it. Both of them are really good ways. So I'll show you right now. What if I asked you to find tangent of cosine inverse of 1/2? And you go, no, please no. Please no. I don't want to do that.
Just pull the inside out.
Oh, you can. Actually, this one's kind of easy. Really, when you think about it, this one's easy. I'm going to give you 2 ways to do it. If it's an easy number like 1/2, a number that appears on your unit circle, you can do it this way. Think about what cosine inverse is. So cosine inverse of 1/2 would equal, let's call it theta. That means that cosine theta would have to equal 1. Are you guys okay with that change? Do you see what I'm talking about here? If cosine inverse of 1/2 equals theta, call it theta. Then cosine theta would equal 1/2. You switch the x and the y. Tell me, what angle gives you 1/2 when you put it into cosine?
Pi over 3.
Pi over 3. So then theta would equal pi over 3. Are we okay with that one? You sure? Well, look at that. This is what we called theta. So we know that cosine inverse 1/2 equals pi over 3. That's what we know. This, is what you put in here. Can you find tangent of pi over 3? Can you do that? How much is tangent of pi over 3?
Put sine and cosine together. Square root of 3 with square.
Just square root of 3. Did I blow your minds with that one? I don't want to blow your minds, but really what we're doing... Huh?
We did that in Trig.
Yeah, you did this in Trig. I just want to make sure you can still do it now that you're not in Trig. Can you still do it now that you're not in Trig? Okay, so we take the inside, cosine inverse of 1/2, no problem. This is pi over 3. Just plug in a pi over 3 to tangent. You get square root of 3. Does that make sense? There is another way to look at this. When these get harder, you can do it this way. From right here, you go, okay, tell you what, let's consider cosine theta equals 1/2. Draw yourself a triangle that has the relationship of theta, of cosine theta. So here's our theta. If cosine theta equals 1/2, please tell me the side relationship of a right triangle for cosine. It is what over what? Very good. Adjacent over hypotenuse. We okay with that one? Find the missing side. Can you find the missing side? Sure. Sure. So, how much is it? This would be the square root of 2 squared minus 1 squared. Square root of 3. Now, find the trigonometric relationship that you're looking for, the trig function that you're looking for. So if we know that this is cosine theta, just find tangent of that. So tangent theta would equal, tangent is opposite over adjacent. Square root 3 over 1, or simply square root 3. So there's really 2 ways to do it. You can do it just directly with it, or you can make a triangle out of it. If you make a triangle, take this relationship, take the inside. Here's the steps. Take the inside. Find the original trig function, right, draw yourself a triangle. Whatever you get out of that triangle, find the trig function of this new triangle, of that angle. And that's very easy. Do you guys want to try one more? I'll show you one that you can't do the other way, that you have to use a triangle for. So, what's the first thing we want to do? Let's take the inside. Let's do sine inverse of 1/3. What are we going to call that?
Sine of theta.
Let's call it theta, yeah. Let's call that theta. So look what we're doing. Look at the board. This piece right now is theta. Does that make sense to you?
Mm-hmm.
So when we draw our triangle, that theta is the same theta. So if I'm trying to find cotangent of this, that's theta. Just find cotangent of that triangle. You're good to go, relating to the theta, the angle that you called it. Does that make sense? So, okay, so sine inverse of 1/3 equals theta, if and only if sine theta equals 1/3. Just switch them. You okay with that so far? Now, there's nothing on my unit circle that has a 1/3. This is going to take a triangle. Sine, give me the relationship for sine. What 2 sides do we see? Opposite. Hypotenuse. Usually you'll have to find the other one, so let's find the other one here. Okay, that would be the square root of
4.
Square root of 2. Square root of
2 times the square root of 3.
that one?
No.
Why not?
1, 2, 3. Square root.
2.
That one? Do you guys know how to use Pythagorean theorem?
Yeah, sure.
Okay. Square this one,
9.
square this one,
1.
subtract them,
8.
put a square root on it.
2.
There you go, you got it, this is it, 2 root 2. Now, find cotangent of theta. Cotangent of theta, look at this. Cotangent of theta is cotangent of this thing. It's the same thing. So this is theta. This is theta. So just find cotangent of theta. Cotangent. Now, if tangent is opposite over adjacent, cotangent is, it's the reciprocal. So we're going to get
Adjacent.
what that means for us is that cotangent of sine inverse of 1/3 is 2 root 2. That's what we're required to find in this problem.
Is there ever going to be any domain restrictions though when we start doing
You
this?
do have to make sure these fit the domain. Now, of course, this is within our domain for sine inverse. Well, between negative 1 and 1.
Negative 1.
Sure, if it's not, then you can't do it. You know what, that's not completely, I'll show you one that we fail the domain. I'll show you how to work with it actually right now. So a couple properties of inverses that we have. Are these. These are all true if the domains are correct. So what we're looking at right here, the x has to be in this domain. So this is only true if x is between negative 1 and 1. Because that's the domain. That's the domain of sine inverse. Are you guys following me on this stuff?
Yeah, it's like a function.
This has the domain of this, correct? So then in order for this to actually work, this x would have to be in the appropriate domain. If it's not, then we got an issue. This works if it's in the appropriate domain. Again, same, negative 1 to 1. This works if it's in the appropriate domain. Domain for tan inverse was negative infinity to infinity. Do you remember these domains from the inverses that we just did? Sine inverse had this domain. Cosine inverse had the same domain. Tan inverse has this domain. Now, check this out. Please look. When we switch them around, the domain changes. So it depends on what is inside and what is outside. Yes, it's true that whenever you have a trig function next to its inverse, or you compose them basically, a trig function with its inverse, a trig function onto its inverse, whenever you do that, yeah, it's undoing it. That's what inverses do. They undo each other. So we're going to get x, provided that this is the argument of your inside function is in the domain of the inside function. So for instance, this has to be in the domain of sine inverse, in the domain of this, in the domain of this. This would have to be in the domain of sine that we restricted. This is no longer negative 1 to 1. It's actually negative pi over 2 to pi over 2. This is no longer negative 1 to 1. It's actually 0 to pi. This is no longer negative infinity to infinity. It's negative pi over 2 to pi over 2. I'll give you just two very, very quick examples about how you would do this. Watch carefully. If I wanted sine inverse of 0.3, here's how you do it. You look here. Is this in the appropriate domain? For instance, this is sine inverse, so is 0.3 between negative 1 and 1? Then this problem's really easy. If this is within this domain, you go, oh, cool. The answer is 0.3. Zero work. A trig function will undo its respective inverse. That is what will happen provided that is in the domain. So if that's between -1 and 1 for my inverse function, booyah, we're done. What happens sometimes though is you get this. Now we can work with it, you just got to work around it. So check this out. Cosine inverse of cosine 3 pi over 2. Two things about it. Firstly, look at cosine 3 pi over 2. Is this in the appropriate domain?
No.
No.
So you cannot do this. This does not equal 3 pi over 2. It's not true. Here's what you do. You think about how much cosine 3 pi over 2 actually is. How much is cosine of 3 pi over 2? It's 0. Then, if you change this to what it actually is, cosine inverse of 0, cosine inverse of, well, okay, that's between there. That's fine. We can actually do that. So cosine inverse of 0, what do you need? What angle do you need to get 0 out of your cosine? Think about it this way if you need to. Cosine of theta equals 0 between, cosine, between 0 and pi. Cosine of what gives you 0, please?
Pi over 2.
Then this is pi over 2. So, it's not 3 pi over 2, it's actually pi over 2. So sometimes even if it's not in the appropriate domain, you change this one. You look at what it actually is. This really is 0. Then do cosine inverse of 0. That'll be in your domain and then you can work with it. Show of hands if you feel okay with that part. Okay, cool. Okay, so we've learned a lot about inverse trig functions already. We learned a few identities, how to work with them a little bit, what the angles mean in reference to our original trig functions. Now we're going to move over to derivatives, and in just a little bit we're going to talk about integrals that involve some of these inverse trig functions. Also, if you ever read or hear arc sine or arc cosine, that's what these mean as well. They're inverses as well. So here's our derivatives. Now they look a little weird. Why in the world do these derivatives look the way they do? I'm going to put them up on the board, and at first you might be kind of curious as where they come from. I'll prove a couple, just 2 of them for you, to show you where these are actually coming from. So here's our derivatives. This is another thing that you're going to want to write down, like on your paper to have next to you when you're doing your homework. I'll talk a little bit later about our tests in this class, but write these down and have these next to you, okay? We're going to need these. So here we go. So sine inverse. Our derivative, if you want to do the derivative of sine inverse, it really doesn't look like cosine or anything. That's not the way these inverses work. The derivative of sine inverse is actually, oh, you know what? Can you do me a favor? Because a lot of these are going to involve the chain rule. Instead of x, what are we going to use?
Yeah,
let's use u. After I have you write them all down, sorry. Change them all to u. So if we want to do the derivative of the sine inverse of u, of course we still need to do our chain rule, but here's how we do it. We put 1 over the square root 1 minus u squared, and then if we have the chain rule, that's when we apply it. 1 over the square root of 1 minus u squared du dx. For cosine, now, do you remember this? You remember how derivative of sine is positive and derivative of cosine is negative? Same thing works here. It's going to look identical, it's just that it's negative. Isn't that interesting? So a lot of the same properties, it looks really weird. So we'll have 1 over square root 1 minus u squared times du dx, but it's going to be negative. Tangent, tan inverse. We have 1 over 1 plus u squared, or you can do u squared plus 1 due to the commutativity of addition, du dx. Cosecant. For cosecant, we have -1, absolute value u, square root u squared minus 1, du dx. Sine is really related to cosecant, cosine is really related to secant. If sine was positive and cosine was negative, tell me the relationship between cosecant and secant. Did you follow that? These two are really related, right? So are these two. These two are related, so are these two. So this is positive versus negative, this is negative versus
Positive.
That's right, it's going to look exactly the same, just with the positive. And lastly, we got cotangent. Notice that cotangent is going to be really similar to tangent, it's just the same thing, only negative. And those are our derivatives. Do you see why I say put these on a piece of paper, have them next to you when you're doing these? Because they're going to be hard to memorize right off the bat, and they're really similar to each other. So have these down whenever you see a derivative of sine u, or sine inverse u, I'm sorry, I misspoke. Sine inverse u, sine inverse of 3x or something. We can use this. Just have that formula, plug in u where it's supposed to go. We're going to do a couple examples right now. Well, in a couple minutes I want to prove a couple of these. But are you okay with the formulas right there? Do you have them written down exactly the way I have them written down?
Yes, sir.
You'll make sure they're all exactly correct, because we don't want to mess up any of these signs, like -1 versus +1, or have anything transposed. Now, would you like to see why these are the way they are? Okay, let me do a proof. We'll prove this one and this one. The others are similar. So proof. We'll do the cosine inverse. Well, let's start off with what cosine inverse of, we'll do x, but if we have cosine inverse of x equals y, this happens if and only if, we did this last time, this happens if and only if cosine of y equals x. Do you remember doing that?
Yes, sir.
Okay. Well, if I consider cosine y equals x, these two things they basically say the same thing, okay? The one's just the inverse of the other. So let's work on this one. This is going to be a little bit easier for us. Let's take the derivative on both sides. Notice that this is implicitly defined. It's implicitly defined because I have y wrapped up in a function equal to x. So let's do some implicit differentiation with it. If I take the derivative of both sides, y'all can help me with this side. What's the derivative of x?
1.
Perfect. And the derivative of cosine y. Keep in mind, this is implicit. So y is a function of x. What would we have to do if y is a function of x here?
Negative sine x times y prime.
Okay, so negative sine, you guys okay with the negative sine x? Derivative of cosine is sine. Not x, but
Y.
Okay.
Times dy dx.
Very good. dy dx because of what? Implicit, which really, that just means a chain rule. We'd have a derivative of y with respect to x because y is a function of x that's not explicitly defined here. We okay with that one? Well, this is really easy. Let's just solve for this. Let's solve for dy dx. If we solve for dy dx, we got 1 over negative sine y. By show of hands, feel okay with that so far? Okay, now, does this look anything like this?
No, but that's
Yeah, well, we could do the negative, right? We could move the negative here. Does that look anything like that? Here's the problem. Sine y, it's still not explicitly defined. It's still implicit. So what we want to do is we want to figure out how much sine y really is equivalent to. So we're going to do this one of two ways. We're either going to use an identity, which is the way I'm going to show you, or you can even use a triangle for this, which is the way I'm going to show you in the next process. So I'm going to do two different processes on these proofs, one using identity, one using a triangle to show you each way. Notice that either of them can be done in either way. So in our case, we could be making a triangle right now like I'm going to do in the next one, but I'm going to use a really simple identity that we really should have down. We should know that if I do sine y squared plus cosine y squared, it's supposed to be equal to how much?
1.
That's a Pythagorean identity. Well, tell you what, let's solve for y here. If I subtract cosine squared, I get sine squared y equals 1 minus cosine squared y. You guys okay with that one? We're almost there. Let's take a square root. Now here's the fun part. Here's the interesting part. First, are you guys okay on working down this identity?
Yes.
Okay, fantastic. Now, cosine y. How much is cosine? Well, let's look back up here. How much is cosine y? Do you see it?
X.
So this part right here, I'll use a different pen. Because cosine y equals x, cosine y squared is, that's exactly right. Therefore, sine y equals square root of 1 minus x squared. Oh, that's where we're getting it from. Do you guys see it now? So instead of sine y, so this said cosine y, hey, cosine y was x, therefore cosine y squared, cosine squared y is x squared. Now I have the substitution, I'm going to put this right here. Therefore this proves that our derivative is equal to negative 1 over the square root 1 minus x squared. Exactly what we have. Instead of u, we have x, but that's the whole idea. Show of hands, feel okay with that one. Did you follow that one? It's not too bad, right? But that's why these look so weird. It's because since they're inverses, when we change them back to original functions, we do our whole derivatives, well, we got to change them back using that inverse again. So we're getting x's out of these because we've defined it as cosine y equals to x. Now let's look at the next one. We'll do, let's do secant. Secant inverse. So proof for secant inverse. If we have secant inverse x equals y, this happens if and only if secant y equals x. Well, that's kind of nice. We already have that. We know that probably we're going to be substituting this back in at the very end because derivatives of secant give you back secant. Are you with me on this one? So we know that this is true because of the definition of our inverses. Let's work with this guy. Again, it's implicitly defined, so we'll take a derivative with respect to x on both sides. Okay, right-hand side, derivative, everybody.
1.
Left-hand side, that wasn't everybody, come on now. Left-hand side, derivative, everybody. Well, that was too fast.
Yeah,
I didn't even hear that. I was like, oh, wow. Secant y, tangent y. Very good. Secant y, tangent y. You all right with that one?
Yes, sir.
Okay, fantastic.
dx, dy dx.
I wasn't okay with that one. What are we missing here?
dy dx.
It's implicit. You have to have that dy dx. It's chain rule. Hey, y is a function of x. So if y is a function of x, you've got to show that by the chain rule. Now, if we solve for dy dx like the last time over here, let's just divide by this. Therefore, dy dx equals 1 over secant y, tangent y. Are you still okay so far? So use this idea. Okay, inverses mean this for our original functions. We should do the inverse. This is defined, this if and only if this, no problem. Take a derivative implicitly. That means with the chain rule, you're going to have to do dy dx. Otherwise, we don't even have a sign for our derivative. That wouldn't make sense at all. Solve for our dy dx. We end up getting this. Now this is a problem because I've got y's and I want x's. Well, one of these is really easy. Look at secant y. How much is secant y?
X.
That's going to give us the x. Now, the tangent y we've got to do just a little bit more work for, okay? What we're going to do, I'm going to draw a triangle. And we're going to look at how this relates in a triangle. So, from here, by the way, I said this earlier, you could have done the exact same thing with cosine y equals x. Here's what you do. What is my angle here? X or y? Y is the angle. What's the angle here? So y is my angle. Now, if you were to think about cosine, cosine would be, what's cosine? That's right, adjacent over hypotenuse. So if you, don't write this down because I'm going to change it in a minute, but just watch for a second. If you were to do the cosine y equals x over 1, cosine y would equal adjacent over hypotenuse. You see it? Hey, look at this. This side is 1 minus x squared. Now, if you took sine of that angle, it's opposite over hypotenuse. Right there. Same thing. Do you see what I'm talking about? Okay, that's what we're going to use, only now we're going to do it here. Did you follow that at all? If not, go back and watch the video next time. You'll hopefully you get that. Now, because we're changing from cosine to secant, we're going to have just a slightly different relationship. Secant is what over what? It's the reciprocal of cosine, so it's not hypotenuse. It's not adjacent over hypotenuse. It's hypotenuse over adjacent. So this would equal hypotenuse over adjacent. Does that make sense to you? Yes, yes? Now, by Pythagorean theorem, we can do this one really easy. This will be the square root of hypotenuse squared minus side squared, x squared minus 1. Are you okay with that one? You can do Pythagorean theorem on your own if you want to. Call that side a or something. You'd have x1 squared plus a squared equals x squared, solve for a. So x squared minus 1, take a square root, you get this thing. Now, what are we looking for? If we try to do secant y, well, we already have it. It's x over 1. That's how we got this triangle in the first place. But this will allow you to find any other trigonometric relationship that's based on the angle y. So if we need tangent y, tan y is, what's tan again? Opposite over adjacent, but the 1 doesn't really matter, so here we go. dy dx equals, hey, look at that, that's positive 1. How much was secant y again? Now, here's what we're going to do. Because x here is the hypotenuse, a hypotenuse can't be negative. It can't be. Even if you were to do this on your coordinate system, that length is always positive. To show that, we put an absolute value. So secant y gives us x. We do absolute value x as a hypotenuse. Tangent, well, we found that. Tangent is the square root of x squared minus 1. And we've just proved, I hope we proved it. That looks right to me. Instead of u's, we have x's, but that's the proof for it. The only reason why you get the u's and the du dx is by the chain rule, which works all the time for functions inside of functions. Show of hands if you feel okay with these ones. It's interesting, right? It's a little weird, but that's why we're getting these weird things. It's just because of triangles. It's just because of this stuff, same stuff. Now, would you like to see how to do this in practice?
Yes.
Probably so. Tell you what, I'm going to move back over here because I want to keep these on the board, so these are going to be here for basically our whole day until we get to integrals. Do you have any questions on the proofs? Okay. Okay, let's see. Well, let's start with this then. Let's try to do the derivative of f of x equals cosine inverse 5x. Now, there's no need to go through all this proof over and over again. These have all been proved. So all we need to do is figure out which one of these 6 formulas we use one of those 6 formulas appropriately, plug in the right stuff in the right place, and make sure you don't frickin' forget the chain rule. Oh my goodness, I'll strangle you. Well, I'm sorry, I'll strangle your papers. I'll punch your paper right in the face, okay? Make sure that you follow the chain rules. A lot of people here go, where am I getting the 5 from? Where's that coming from? Why is the answer wrong in the back of the book? You're wrong, book. No, the book's right. It's just you're forgetting the chain rule a lot, okay? It happens all the time. So, when we do this, which one does this fit? First one, second one, third one, fourth one, fifth one. Obviously, it's cosine inverse. So, the way we do derivatives of cosine inverse, if you want to do f prime of x, remember that notation? It's a long time ago. What this says is that, well, what's our u in this case? Yeah, that's just the inside. It's just a chain rule. So cover it up. Go, okay, this means I'm going to have -1 over, there's going to be a square root there. 1 minus, I'm sorry, what was the u again?
5x.
Put the 5x here. What do you need to do that 5x? Okay, don't just square the x. Don't put 5x squared. It's 5x quantity squared. It's got to all be squared. So this would look like this. We plug it in without doing math in our head. And then we do one more step after this, okay? So we're plugging this in. We're going to have to do chain rule anyway to show that. So you may as well not do this in your head. Sometimes you get to, but for right now, I want you practicing this. And then we do derivative of whatever you, oops, I wrote you. Whatever you just plugged in. These should look the same all the time, every time. Does that make sense?
Yeah.
Okay, so the derivative with respect to x of the function f is -1 over, oh, well, calculus is basically done here. 1 minus 25x squared times what?
5.
Yeah. Notice if you forget the chain rule, you're forgetting a 5. So to clean this up just a little bit more, we would put -5 over square root 1 minus 25x squared. That's our derivative. Is it straightforward enough for you guys to understand it?
Yes.
Since we've proved these formulas, I know they look weird, but you can use them. It's just a formula. That's how we're doing derivatives of these inverse trig functions. Now, of course, we're going to make things a little bit more complicated more and more, okay? This was an easy one. We're going to start building this stuff up little by little. So let's practice some more here. Do you have any questions before we go on?
No.
Okay. All right. Let's find the derivative with respect to t of sine inverse of the square root of 2t plus 1. And you go, oh man, there's lots of stuff in there. Well, firstly identify what you're dealing with here. We're dealing with an inverse trig function, which means it's going to be on that list. So on this list, we're going to look at which one it is. Of course, this is the very first one we had. This is sine inverse. So the way we go through these, this is the last one I'm going to do for you, just telling you how to do it. After this, I'm going to ask you some questions about it. The way we go through this, we first write out the formula identifying what our u is. The u is always just the argument or the inside of your inverse trig function, just like it is any other chain rule. So what is our u here? Does it include the square root?
Yeah.
Yes, it does. It's the whole inside of that inverse function. Are you guys okay with that one?
Yeah.
So this is going to be, let's see, sine. Is sine positive or negative? So we got 1. We got a square root. We've got a 1. We got a minus. What do I put next? 2t plus 1. And then what do I do? Well, that's interesting, isn't it? So don't forget that this thing is squared. It really should look like this. This is why we don't do things in our head right now. Right now, we're writing this out exactly like our formula says. 1, 1. Square root with a 1, square root with a 1. Minus, minus, and then u. Okay, I got u with the square. And then I'm done, right?
No.
What do I need?
Chain rule.
Chain rules it. So times the derivative with respect to t, make sure your variables match here, of the square root of 2t plus 1. You know what? I don't like the square root of 2t plus 1. So I'm going to do 2t plus 1 to the... Oh, I love this stuff. What do you need for that one?
Chain rule.
Chain rule. There's, man, you guys, you got to understand, in calculus 2, we have chain rules and chain rules and all the time we're getting this stuff, okay? It shouldn't be hard because you did this. You did chain rule a lot in your last class in calculus 1, but we're going to practice a ton of that. So let's keep on going. I know we got 1. I know we got a square root of 1. What happens here?
That radical cancel out.
Okay, please be careful on your algebra. Square root with square, yes, that's gone, but don't do this. You do that, you get the problem wrong. Why? That? Yes, that's what we're talking about, okay? That minus, that's going to distribute. Now, times, let's do the derivative of 2t plus 1 to the 1/2. What do we do with that?
Bring the 1/2 down.
Sure, it's our chain rule. It's a general power rule. So 1/2, we got it. Do we do the derivative right now of this?
No.
2t plus 1 to the negative 1/2. I wrote that poorly. Let me rewrite that. Negative 1/2. I like to be nice and neat here. And then we're done?
No.
T dx 2t plus 1.
All right. Times what? Derivative. 2t plus, finally, oh my goodness. Do we need a chain rule for this one?
No.
This is easy. Okay, we finally got down to an easy one. Okay, so we've got a 1. We've got a square root. We've got a 1 minus 2t minus 1 minus 1. We've got a, let's start cleaning this up just a little bit. Let's put the 1 over 2 square root, very good, that moves down to the denominator. 2t plus 1 times derivative of this whole thing is 2. That's 2. Tell me some good things that happen.
The 2's reduced.
2's are gone. They simplify. Tell me something else that happens.
So 1's
The radical is here too.
Look inside your square root. What happens here?
these.
1's are gone. That's right. 1 minus 1 is 0, so we've got,
Isn't that just t?
say what now?
Wouldn't the square root of 2, no wait, no, it's negative.
Not just t, it's actually negative 2t. Twos are gone. We could actually make this all in one fraction if we wanted. Do 2t plus 1. That's it. That's our derivative. Can you handle it? Show of hands if you can. If you're okay with that one. Good deal. Okay. Now, we're going to build up a little bit. We'll get to some things that are a little bit more interesting, which means, yes, a little harder, more advanced concepts. Question?
Can you have a negative in the square root?
Yeah, but you got to keep in mind what your t can be defined as right here, okay? So your t would have to be negative, but not so big as to make this negative. So it's a really small defined t, okay? Good question. Any other questions besides that one?
This is probably just an algebra question, but you wouldn't be able to multiply those two together.
You actually can, yeah. You could, because you have a square root times a square root, you could do that, distribute it. I would leave it, it's fine just like this. Okay, moving on. How about we try to conquer this one? As you can see, there's lots going on in this problem. So let's go through it step by step to really make sure that we get it, okay? Tell me the first thing that you're looking at here.
Look at the y.
Say what now?
The y.
The y. What do you mean the y?
Because it's a y. I would think it'll go ln now. But
Well, you know, the y is just saying we have a function. So I don't care about this one because if I do the derivative of y, it's just going to be dy dx. So the y is okay. We're okay on that side. I mean on this side where all the nastiness is.
E.
The e. Okay, so what are we going to do first? We take the derivative of this or the derivative of this? Yeah, because it's a chain rule. It's going to be like two chain rules like we had last time. Would you see the two chain rules I'm talking about? We got chain rule because it's not just x. Then we've got chain rule because it's not just x. We get two of them. So dy dx equals, let's look at secant inverse. So find secant inverse on your formula sheet or on the board as I've left it. Secant inverse says we do what? Positive 1 or negative 1? Positive. So we're going to have positive 1. It says we do absolute value. Absolutely. Absolute value. What goes inside of the absolute value? Yes, that's right. Whatever's here. Argument of your inverse trig function goes there. No matter what it is. It doesn't matter. You don't change it at all, ever, for this part. E to the negative 2x, and you just close it off. Well, that's fairly easy. You're just following a formula. Then what do we do?
Square root.
Square root. I got the square root. Oh man, I'm going to run a room. Square root, what goes inside?
Minus 1.
That's right. Okay, so argument squared, all squared. Make sure you get parentheses, all squared, and then what?
Minus 1.
Minus 1.
And then d is
Derivative, oh yes, a chain rule. Derivative of what?
The negative 2x.
Are you starting to see, I know that many of you are you starting to see how important the chain rule is? You use it all the time. Starting to see how you can't forget about it? If you get little pieces, your problem's blown. I mean, you screwed that problem up. The paper starts crying. Please don't, you're ruining me. What you've done to me. That's when I go crazy after I start grading like 14,000 tests. Oh my gosh. I start making stuff up. Anyway, so let's see if we can simplify this a little bit. So we have dy dx equals 1 over... Does that change?
Can you bring it up? Oh wait, no. Never mind. I can't see.
How about this one? Can we simplify that a little bit?
You can multiply. You can
the exponent secant.
Yeah, exponent raised to an exponent.
Squared.
Hello? Exponent raised to an exponent u.
multiply.
So negative 2x times 2 gives you... Cool. Let's do this derivative now. Let's all do that. I want you to do it on your own. See if you get the right thing. Derivative of e to the negative 2x. We haven't practiced a whole bunch of those, but we should be getting pretty good at them.
Negative 2.
Did you get the e to the negative 2x back?
Yes.
Times negative Derivative of 2.
Yeah.
Negative 2x.
Yeah, chain rule says this. So dy dx says, all right, well, let's look at some nastiness here. We got absolute value e to the negative 2x. No problem. We got a square root e to the negative 4x minus 1. Got it. We've got an e to the negative 2x. And then via the chain rule, we got, what's this one?
Negative 2.
I'm going to put that in parentheses showing we're not subtracting. It's a negative. Show of hands feel okay with that so far. We're going to clean it up a little bit and talk about some pieces of this. First piece. First piece. Talk about the absolute value here. Talk about the absolute value. E to the negative 2x. Is that ever negative?
No.
So we can drop the absolute value because e, any base to a power, no matter whether it's positive or negative, is always positive. So this is always going to be positive. Are you clear on that one? So absolute values are gone. Also, let's bring this forward. I've got negative 2e to the negative 2x. I now have here, without absolute value, e to the negative 2x. I've got a square root of e to the negative 4x minus 1. Anything else we can do?
Cancel out.
Can you? Can you?
Yeah.
Is that being multiplied?
Yeah.
Is that being multiplied?
Yeah.
Did we get rid of the absolute value?
Yeah.
Yeah, you had to. In order to do this, by the way, you had to get rid of that. They're exactly the same. Simplify like you know what you're doing. Let's simplify those things. So our derivative becomes actually quite nice. We get negative 2, relatively nice, e to the negative 4x minus 1. We're done. That's the whole idea. So some simplification here, but really the idea is use the formula. Don't forget the chain rule because you can have chain rules within chain rules within chain rules. Feel okay or no? Yes.
Explain one more time why you dropped the absolute value.
It can never be negative.
This is never negative. Think about it. E either goes asymptotic to the x as x approaches negative infinity, or asymptotic to the x as x approaches positive infinity. Either way, it's not dropping below the x-axis. It's never negative. So drop the absolute value. You don't need it. Let's do one more, and then we're going to talk about the integrals. This is about as advanced as I'm going to make it for you right here. So if you can do this problem, good to go. I know. That looks nasty. Let's talk about what's going on here. Firstly, write it down, of course, but then let's talk about what's going on. First thing, what do you see smacking you in the face? Question? What do you see smacking you in the face right now when you see a problem?
Two chains.
A function, which means that you're going to do
The outside first.
chain rule. Yeah, outside first, chain rule. This is a chain rule. This is now the argument of cotangent. Do you see it? Inside of this, you're going to have another chain rule. So let's see how this thing works out. This is not one time where you're going to want to do everything in your head, okay? Do steps here. Follow the ddx in this case, and see what it gives you. So dy dx, if we're taking a derivative, it says, with chain rule, take the derivative of the outside function, leave the inside alone. What's the derivative of cotangent, please? Remember, cotangent is not this. This is cotangent inverse. I'm not looking at this. I'm looking at the cotangent that you should have in your head already. Good. So this is negative cosecant squared of whatever this is. And then am I done? Okay, now what am I going to do? Chain rule with regards to just the x squared or this whole thing? Yeah, that's right. So, chain rule, no problem. Derivative, leave inside alone, multiply by derivative of the inside. That should be no brainer. We're okay with that. Okay, so this equals negative cosecant squared cosine inverse of x squared. Oh, goodness gracious. Times, okay, now we're going to do the derivative of cosine inverse x squared. Do it. Right now you should be good enough to do it. It is a chain rule, so that's the only advice I'll give you. But go ahead. I'm going to run the board, see that you guys got the same thing on your own, okay? what I really want to know is, did you get a negative 2x as well? Did you get a negative 2x? Somewhere. Did you get a negative 2x? If you did, you did the chain rule appropriately. If you didn't, you kind of messed something up. So let's verify. This is cosine inverse x squared. We're going to take a derivative of that. That's this part, negative 1 over 1 minus u squared. Did you all get that one? X to the fourth there. And then derivative of the inside is 2x. When we do this, we get negative 2x over square root of 1 minus x to the fourth. We okay with that one?
Yep.
Now, this looks fine. This looks fine. This right here, I want to look at this one a little bit. We're going to talk about that for a second. So let's see if we can manipulate cosine inverse of x squared using that whole triangle thing that we did before. So little sidebar. Cosine inverse of x squared equals, let's call it theta, okay? Because what we should know about inverses is that what an inverse function equals is an angle. Does that make sense to you? It's an inverse. So this happens if and only if, awful triangles there, if and only if cosine theta equals x squared. Can you follow that logic?
Yeah.
Just switch them. Now let's draw a triangle. Make that a theta. Think about cosine theta. Cosine is what over what, please? Adjacent over hypotenuse. Okay, x squared for our adjacent, 1 for our hypotenuse. Does that make sense to you?
Yeah.
Okay, now, let's fill out this. Let's fill out this. So, why don't you solve that, if you can? Square root, I'll give you the square root. This squared minus this squared. 1 minus x to the fourth. Are we okay with that one? Now this is interesting. Check out what we just did. So I'll do a 10-second recap for you, just so you see what's going on. Are we okay to do the derivative down to here?
Yep.
We probably should be, right? Looking at this little piece, cosine inverse x squared, we say, okay, call that an angle of a triangle. No problem, it has to be because it's an inverse trig function. This happens if and only if this is also true. This is a 1, by the way, that must be a t, but that's a 1. Well, that means that our adjacent x squared, our hypotenuse is 1, we can solve for a missing side by Pythagorean theorem. Now think about what's going on here. We just called this thing theta. Does that make sense? This angular relationship for theta, or this side relationship for theta, for our angle theta, if this is theta, I want to find cosecant of theta. Then square it and make it negative. So what I'm looking for now is cosecant. Are you aware that this is theta? Does that make sense to you? That's what we call theta. That's how we got our triangle. So if this thing is theta, let's just find cosecant theta. Cosecant theta. Cosecant comes from sine. So if cosecant comes from sine, it's the reciprocal of sine. Hypotenuse over hypotenuse over opposite. I'm going to show hands if you're okay with that one. It's a little weird, right? We're using a triangle to our advantage, though. We're saying, yeah, the sine would be this over this, therefore cosecant is this over this. No problem. Do you see how to use that? It's kind of cool, right? Using the inside to make a triangle, then finding cosecant of that angle of your triangle that you just found. It's awesome. Now, we don't really want cosecant theta itself. We want cosecant squared, and then we're going to make it negative. So if I want cosecant squared theta, all I have to do is square the numerator and denominator. That means I get 1 over 1 minus x to the fourth, because if I square this, I square this. 1, and then square root's gone. Are we okay with that one?
Yeah.
Last step. If I want this to be negative, put a negative. So negative cosecant squared theta gives you negative 1 over 1 minus x to the fourth. Now let's put all of this crap together. This piece from our triangle is negative 1 over 1 minus x to the fourth. This piece, that's easy. This is negative 2x over square root 1 minus x to the 4th. You ready for some fancy pants math? Read a little bit of fancy pants math. You ready?
Yeah.
Okay. When you have x to the first times x to the 1/2, we get x to the 3/2. Agreed?
Yeah.
As we add. That's what we're going to do here. This is to the first power. This is to the 1/2 power. Therefore, when we multiply, we're going to get a positive 2x, and we're going to get 1 minus x to the 4th to the 3/2 power. And that's it. That's as simple as we can make that one. What I'm really concerned about is that you can get down to here as far as your derivatives. Did you understand that?
Yeah.
And I'm also concerned about, because we're going to use a lot, this a lot, this idea of making a triangle and using a triangle. Did you follow that? It's interesting though, isn't it? It's a little bit bizarre because maybe some of you hadn't done that before, but you see that it's possible. Hello, yes, no? Yeah. You sure? All right. Let's talk about one more, move on to integrals, and I'll wipe off the whole board here.
So on a test, if
This is what I want.
we want it all the way down.
Yep.
So we have to
Yep,
check
you
if she would try.
gotta know, you gotta do that. So maybe it would behoove you to practice this a couple times. Really come by and see me if you need to, watch a video again, practice that a few times. Get in the triangle on your own, okay? Don't just follow my notes. Do it on your own. Okay, one more. We'll talk about this. If I asked you to do the derivative of tan inverse x plus x cotangent inverse x, could you do it? Can you take the derivative? Do you have to do this all at once, or can you do this piece to this piece?
That piece and that piece.
Good, we can separate by addition, that's fantastic. Can you do the derivative of tan inverse x?
Yeah.
That's really easy, actually, no chain rule at all. What would you have to do for this derivative?
Product rule.
Good. This one would be easy, this one you have it right on your formula. So be aware of things like that and we should be good to go. Do you guys feel okay with our derivatives?
Yeah.
Okay, now I want you to notice something here. Look back at our derivatives. Do you see that there's really only 3 different types of derivatives and the other 3 are just negatives of them?
Yeah.
Identical, just negative. Identical, just negative. Identical, just negative. What that means is that we really only need 3 new pieces of our integration table. What we're going to do is we're going to take this one, we're going to take this one, and we're going to take this one. So we're going to be able to find the integrals of here, here, and here, because if they were negative, you just pull them in front of your integral anyway, wouldn't you? I would. So here's our new integration table. We only need 3 because the other 3 are negatives of the rest. Let's say we have an integral and we can make it 1 over square root of 1 minus u squared du. What are we going to get out of that? Let's find it. Which one's it like?
That's a sine.
That's, well, not quite sine.
inverse.
Sine inverse u plus c. That's exactly right. What are you going to have to do a lot in these next problems, do you think? You're going to substitute like mad dogs all the time. Substitute, substitute, substitute the whole time. Okay, how about we do 1 over 1 plus u squared du. What are we going to get out of that? Integral. If we can make it look like 1 over 1 plus u squared du, it's going to become tan inverse. If derivative of tan inverse gives you this, the integral of this gives you tan inverse. Now, because we get a small difference between this and this, I want to show you that. When we do 1 over this doesn't look exactly like this one, but it doesn't matter. Because of the domain of the secant inverse, what happens here is we don't actually have to have the absolute value, but we do get them in our secant. Like that. Just because it's a domain issue. Are we okay with those three? So if we get something look like this, get sine inverse. Something look like this, tan inverse. Something look like this, because it's just like that one, we're going to secant inverse. If you had negatives, check this out. Yes, you could call that, what one would be? Cosecant inverse. But for us, we just pull the negative outside, call it negative secant inverse. That's all I did. Shall we try some?
Sure.
I'd like to do it right now and not next time, just so it's really fresh in our heads. This whole idea. Of course, we'll start out really easy and gradually build up to where it's harder.
You mean more fun?
More fun, yeah.
One way to look at it.
Now, of course, what I've told you is that if it doesn't look exactly like something in your integration table, which you've just added to right now with 3 new integrals, if it doesn't look like that, what do you need for it? So we're going to have to do a substitution. Here's the idea. Your goal is to try to make this thing a 1 minus something squared. So for us, one idea would be, let's leave the square root, we'll leave the 1 because that's great, but you need to write this as something squared and then make a substitution. So instead of 16x squared, I don't like that. I want something squared because that little something there, that's what we're going to call the u. That's why it's defined as a u over here. What's going to be in there?
4.
Yeah, that's exactly right. And now a substitution is just so nice. Don't forget the substitution here. But if we do u equals 4x, then du equals 4dx, or du over 4 equals dx. Notice what I'm not doing. You looking? Notice what I'm not doing. I'm not doing a whole substitution right here. If I tried to do that, I would get an x. Do you see any other x's up here? Be stuck. So we have to have these inverse trig functions to be able to do some of these integrals. It's really interesting. We can't do this any other way than what we have with our inverses here. This is the integral. So we have this, we got, okay, well no, let's make it work. So let's call that, instead of 16x squared, 4x quantity squared. Do a little substitution. Are you guys okay with the substitution?
Yeah.
Now we still have the 1, we still have the square root, we still have this one, we still have the minus, but how much is this now?
U squared.
And that's exactly what we want to see. And instead of dx, we have what?
Du. And then the 1/4 on the outside.
Good. Du over 4, and then sure, with the over 4, let's make that 1/4. So 1/4 integral 1 over square root 1 minus u squared du. Hey, look at that. That's what substitution does for us. It makes things fit. So if this fits, which one does this fit? Is this the sine inverse, the tangent inverse, or the secant inverse? So this says we're going to have 1/4 sine inverse u plus c if you want to right now, which equals 1/4 sine inverse. Why am I not stopping at sine inverse u? Why am I not doing that? We started with x's, right? We want to end with x's. So instead of sine inverse u, we're going to have sine inverse of what? That's right. Let's see. That, my friends, is the whole idea. Let's start one more, make as much progress as we can, and then we'll call it good. Check out this one. Integral of 1 over square root 25 minus x squared dx. Does this look like this? No, so we're going to have to do a substitution, but I want to show you this one because this happens. Some books, some formulas are actually allow for this case, and they'll show you a different integral table for this. I'm a simple guy, I'm a simple man. So what I like to do is I like to make it fit perfectly, and how you can do this, just watch along, how you can do this is force this to factor, force this to be a factor, and do something like this. Instead of 25 minus x squared, do 25 times 1 minus x squared over 25. Do you see that we can force that to be a factor that way? Just divide out the 25. If you distribute, you'll notice this is 25 minus x squared. The 25s would go away. Does that make sense? Hello, yes, no?
Yeah.
Now what this allows you to do is break up this square root. So we're going to do two steps here. We're going to do 1 over, well, here's the square root of 25. How much is the square root of 25?
5.
That's great. Times the square root. Don't forget about that second square root. You're breaking this up by a product. 1 minus, and I'm also going to make this into a square. So instead of x squared over 25, I'm going to think about this as something squared. What is it?
X over 5.
X over 5 would work great. So, little recap. We've got 20, no, I don't like 25. I want to make that 1. I want to make it 1 so that it fits my integration table. So I'm making this into a 1 by forcing it to factor, forcing the 25 to factor out. Are you following me on that one?
Yeah.
Yes, no?
Yes.
Do you see that it is the same thing? Separate your square roots. Get rid of that number. Get rid of that square root of 25. Whatever constant you have factored out, just smooth that out. Even if it's not even a perfect square, you can still do this. It's just awkward. It looks a little worse.
Oh, because it's a constant.
Constant.
Yeah.
Now, square root of this, well, no, I don't like x squared minus 25. I need something squared so I can make a substitution. You follow?
Yeah.
Okay, so what we do, we say, all right, how much is our u going to be?
X over 5.
If we have x over 5, then du equals 1/5 dx, and 5 du equals dx. Almost done. Stick with me. Okay, I gotta wrap things up. So here's 1. How much is square root of 25, everybody?
5.
So we get a 5 here. I've got a square root inside my square root. Please tell me, inside my square root, what do we got?
1 minus u squared.
And instead of dx, I have...
du.
Oh no, it's not just du.
5 du.
Look what happens. A lot of the times this happens here. Do you see what happens?
The 5 cancel.
5s are gone. That's awesome. 5s are gone. We have the integral of 1 over 1, the square root of 1 minus u squared. How much is the integral of 1 over square root of 1 minus u squared? Sine it. That's on your table. So this would be sine inverse u plus c, or wrapping it up, sine inverse of, let's do our substitution again, x over 5 plus c. Did that one make sense to you?
Yeah.
So even if it doesn't quite work with the 1, factor the constant out. Make it factor. If it factors, you can get rid of that constant, square root of whatever number you have. Pull it out front. Oftentimes what happens is when you substitute back in, this number will match up with that number. A lot of the times you can cross it out and then just do a very basic integral. So last time we learned all about the integrals that give us some of these inverse trig functions. We got a couple more examples and then we'll be done with our section. So let's look at the integral of e to the x over e to the 2x plus 1. Now on first glance you might be thinking, well, let's just use a basic substitution and be done with this thing. Well, let's take a look at that. Is a substitution going to work for this? What do you think? If I substitute for this, if I make that a u, is this going to get rid of that?
No.
If I make this a u, is this going to get rid of that?
No. Yeah. I'll say the whole thing.
Well, you didn't get you have 2 back.
I'd have something else though.
2.
So I get this back again. Do you guys see that?
Yeah.
So no, not quite. That would be kind of an issue here. So what we're going to do instead is we're going to try to rewrite this to make it fit one of these things. Do you remember doing that? When it doesn't fit your integration table exactly like that, we're going to rewrite it. We're going to try to make it fit something. Here's what I'm seeing. The reason why this is, for me, this is noticeable is, okay, I see a plus 1. I like plus 1. I see something being squared. Do you see what I'm talking about? Something being squared. So instead of doing just a regular substitution, we're going to make it so that when we substitute, yeah, it's going to be a substitution, but when we substitute, it's going to fit one of these things. So let's break this down a little bit. So yeah, this isn't e to the 2x, this is e to the x. Yeah, we can do that because when we take exponent to exponent, we multiply. Therefore, 2x as an exponent becomes x and then squared. You guys okay with that one so far?
Yeah.
Now check it out. When we go through and do our substitution, let's substitute for the appropriate thing. What is our substitution here? Wait, the whole thing or just this thing? Just this thing. And why we're doing just this thing is because we want to make it fit that thing. Well, that's going to be kind of nice. If I take the derivative of that, what's the derivative of e to the x, please? And dx. Oh, look at that. This is this. We can just do a straight substitution. So our integral becomes, tell me what it is. What's on the numerator of my integral?
1.
Yeah, or what could you put? Put du if you really want to do that. What's on the denominator?
U squared plus 1.
And then,
du.
yeah, don't forget you have to match up your variable. This is not irrelevant. This is why your calculus 1 teacher made you put du or dx or d whatever. You have to match that up. Show of hands if you're okay with that so far. Does it fit now?
Yes.
It's a piece of cake now. Which one is this?
Tangent.
Tan inverse u is what that is. It looks exactly the same. It's only, well, it's a distance commutative, no big deal, but it looks exactly the same. Plus c if you want to right now or later. Tan inverse, one thing we have to do though, we have to substitute this back in. E to the x plus c. You feel okay with that?
Yeah.
Show of hands if you feel not so bad. Awesome.
Not so bad.
Not so bad. Not so bad. Not so bad. Any questions on that one?
No.
These become pretty easy when you know what you're looking for. For instance, I know I'm dealing in a section that has inverse trig functions. Hello, I'm going to try to make it like one of these. When you're not, when you're just doing problems on your own, like I gave you on a test, it might be a little more difficult. So you really do need to practice looking at these problems, identifying, man, what am I going to do with this thing? Try to make it fit. Have your integration table next to you. Be looking at it going, well, how does this best fit? If a substitution doesn't work right away, try something else. Don't force it if it's not working. Okie dokie,
So
question.
you're able to do that because of exponential, right? Because that's like just saying 2 times x.
Yeah. E to the 2x is e to the x squared.
Sounds good.
And that's how I'm looking at that. Okay, last one, let's look at it. Does it look anything like anything in our integration table?
Kind of like C.
It has.
Kinda. Well, it's got a square root, right? So it's not this. It's either this one or this one. Let's see if a substitution would work. How about this one? Look at this. What does substitution work?
Yeah.
Possibly.
If the x was here, absolutely, yes. Do you see why?
Yeah.
The derivative is 18x. Do you see that? X's would go away. If the x is not here, if the x is here, oh, wait a minute, that's, sorry, my bad. That's 1 over x. No, the derivative of this is not 1 over x. Does that make sense to you?
Yeah.
The derivative of substitution has to be there. If it's not, then it will not work. So let's try to manipulate this thing into looking like one of these. So, what's your first idea? What do you want to do?
Change the radical to a 1/2.
Make 9x squared to look like something x.
Very good, because we like the square root, don't we? We're not going to change that. We don't like the 9x squared. We like the -1, don't we? Do you guys see that? We like that one. What we don't like is the fact that this is not something being squared. So change it to something being squared. And someone said it already. What is it?
3x.
That already looks a little bit better. But does it fit exactly our paradigm for this over here?
Not yet.
Okay, yeah, good, substitution. So let's do that. If we do a substitution, please watch carefully because something kind of interesting happens here. When we do a substitution for 3x, yeah, du equals 3dx, or du over 3 equals dx. You guys okay with that one? On the numerator, we got 1. On the denominator, be careful, what do we have? Oh, before that. Did we take care of that x?
No.
That's a problem.
X.
So x, do we still have a square root? Yeah. What's inside?
U squared minus 1.
And then instead of dx, we have
Over 3.
3.
perfect. Show of hands if you feel okay with that so far. So, same idea as last time. We're saying, no, I don't like that. I'm trying to make it fit. Try to make it fit one of these things. Since I see a variable outside, it's not this one, it's not this one, because that doesn't have a square root. It's mostly like this one. We're going to try to make it fit this one. Now, here's the issue. This looks really good. I did my substitution. I've already done away with the dx. I've already done away with the 3x. I got a u squared minus 1 that looks perfect. I've got a du. This is the problem. Do you see it?
Yeah.
Your variables have to match here. They all got to be the same. So one thing that you can do, use your substitution again. I'll say it again. Use your substitution again. So for instance, if u equals 3, please listen and watch carefully. If u equals 3x, that also means that x equals u over 3. Does that make sense to you?
Yes.
Ah! Can you now get rid of the x? Okay, so 1 over x, no, you can't have this, so use your substitution again. 1 over, I'm going to draw it in purple, that way you can see what I'm doing here. This x, check it out, this x is u over 3. U over 3. Well, the u squared minus 1 was great. D over 3, no big deal. So the idea again. Firstly, are you okay with doing the first step? Are you okay that we're picking 3x as our substitution?
Yeah.
Kind of have to, right? If we do that, then we can also make x, just solve for x. X now equals u over 3. That allows you later to change any variables, extraneous variables that aren't u's, into u's. So x now becomes u over 3. No big deal. Now it fits. Tell me what happens with our 3's.
Oh, you cancel out.
They're gone. They're gone. This is over 3. This is like over 3. Ha ha ha. So if you can reciprocate that up, this actually moves to the numerator. That's denominator. They're gone. Well, this is pretty easy then. This integral now becomes 1 over u square root u squared minus 1 du. I need a quick head nod if you're okay with that so far. Does it make sense? It's interesting, right? It's a little bit tricky because you got to do some of that x. You can't leave it. So use your substitution again. No big deal. Now, does that fit our integral model perfectly? How much is it?
Absolute value 3x plus c.
Arc secant absolute value u plus c. Very good. And of course, we never leave that. We're going to have secant inverse absolute value. What's in there?
3x.
That, ladies and gentlemen, is the correct integration. Should fans feel okay with what we've talked about? That basically wraps it up. That wraps up this section. So what I'm expecting from you is that you're able to find these type of integrals. Nothing super crazy right now. Yeah, they're going to be a little bit harder on your homework. Some of them, a lot of them will be just like this. I really just want to make sure that you're getting used to the idea of substituting to make it fit your integration table. We just now have 3 new integrals that we can work with. Any questions or comments, or do you feel good about it?
Good.